But I think, oh, that's loud. I think we can probably start. First of all, thank you very much for coming back this time. I packed the hall with my friends and relatives last time. So I was afraid that it would be half empty. It's still a bit loud. Wind it down a little bit. That's better. So I think just before I start the lecture, it would be a dereliction of my duty if I didn't say something about the comet that's in the sky. Has anyone actually seen a comet in the last few weeks? A few of you have. In fact, very sadly, I found out about it, I think when I got home from my last lecture. So it's been there for virtually 4 weeks. It's called Comet Holmes, and if we could have the main lights out, or as many as we can, that will certainly help. You can see it, perhaps now easier with binoculars, but in the east, in the 8 o'clock mid-evening, sorry, I've got a green pen, sorry. You can see the W-shaped constellation of Cassiopeia. And if you just run straight down towards the horizon, you will see a fairly bright star called Murphak in the constellation of Perseus. And the comet is just to the lower left of Murphak. When it first started, and I'll show you a few pictures, it was as bright, almost as bright as Murphak, and those stars there made a little triangle. In fact, on November the 19th, it will actually go in front of Murphak, this bright star here. That's where the comet was yesterday. To be honest, it doesn't look quite as bright as that now. When it first started, why do my virus scans always want to come up? When it first came up, it was down over here, and it's gradually moving upwards, and it's just the lower left, and on the 19th, it will probably encompass the bright star Murphak. This is a picture taken by one of my friends on the 28th of October. That was the first clear night after we learnt about it. This is the coma, as it's called. The little spot in the middle on the left is called a false nucleus. It's not the nucleus. The comet's probably about 2 kilometers across, so you couldn't see it. There's a little bright spot around it, which has still remained. And it looked very star-like then. It just looked like a bright star. But over time, it spread out in size. This was on the 31st of October, and you can see this outer coma. It's probably not that bright there as well, the bright inner part. And that's the picture I took just 2 nights ago. It's actually not really dark in here, but there's an outer coma there. That's actually a star, but above it is this little nucleus, and the tail of the comet sort of coming out this way. There's actually a very sharp edge. You might see it better from in front. So it's been quite fun. It seems to have undergone an outburst. It shouldn't really be as bright as this, but wonderfully it is. And that's a very dramatic picture taken a few days ago, showing the inner part of the coma, the outer part, and even a little bit of a tail. But the tail's going away from us because it's actually going away from the sun. So maybe there's still a chance to have a look. So let's have a look at colour in the cosmos. How do we observe colour, and what's it tell us? Let's have a look and see. Our eyes, they're very wonderful things. And of course we can see in colour. When you use your eye in the daytime, and at night as well for that matter, the lens focuses the light on the rest of it, and in particular on something called a fovea. I'm sure you know that we have 2 light-sensitive elements in our eyes. Rods, which are only sensitive to black and white, they're not coloured, and cones, which are. But sadly, the cones need more light to make them work. They don't work at all well at night, which is why we don't really see the lovely colours that I'm going to show you in some of the photographs. Okay, we can see the colour of an eclipsed moon. We can see the lovely greens and even the reds of the aurora borealis. And I'll be looking at this in one of the lectures in the new year. But sadly, we can't normally see colour with our eyes. I mentioned 2 exceptions as we go through. What we now tend to do is to take colour photographs. It used to, of course, done with film, but to be honest, nearly everybody now are using CCD arrays, either in cameras or in special astro cameras, as we'll see. You can make colour cameras, and they work just like our colour compact CCD cameras, digital cameras. You have a mosaic of filters which cover the actual photo detectors. Half of them detect green, quarter red and a quarter blue. It's called a Bayer matrix, and you can combine all that data to make colour images. But more normally, people are using a monochrome camera because it's more sensitive, and having a set of filters to get 3 colour images. That's a relatively cheap one, about £500. This is probably costing something like about £2,000, if not £4,000. And you can see there's a little wheel, called a filter wheel, to put the different colour filters in front of the CCD array, which is sitting there. Now, I just did a little experiment at home with my not very high quality system. I was taking some pictures of a painting that I have of roses. That's in the red filter, that was in the green filter, that was in the blue filter. You can see some changes. If you combine those together, that's the first step. You go, and by a little bit of tweaking, then you actually get a colour image. So that's how we do it. This is the sort of equipment used by the people that do this seriously. There's a telescope. This is the main telescope. That's the camera. And this is a cooling system to cool these CCDs down. But then you have a second telescope that's basically called a guide scope that gives controllers to the motor, gives control to these motors to make it track very accurately across the sky, so you can take very long exposures. And in fact, that photograph of the Whirlpool galaxy was taken with the setup that I've just shown you. Now, one thing that we can see with our eyes is that some stars show colour. We can see some oranges and reds possibly, but basically orange. We can certainly see some white stars, and Capella, which is below where the comet is, looks distinctly yellow. I'm going to come to this little plot 3 times. It's a lovely part of the sky. Deneb is the brightest star in Cygnus the Swan, Vega the brightest star in Lyra, and Altair the brightest star in Aquila. I think it was Patrick Moore that called this the summer triangle, but it's still visible fairly high in the west as it gets dark. Halfway down this line, 2/3, just there, is a rather lovely group of stars. It should be called Blockie's cluster, but most of us call it the coat hanger. It looks very sweet. Now, I hope you can see that we really can see some colour here. That star is obviously red, these are blue, that's white, that's sort of orange, and that's sort of yellow. Can you see that better from where you are? Certainly on my computer screen. So we do have colour in the stars. Incidentally, most photographs don't actually show this very well because the stars get burnt out. And what people do, and you'll see a few more examples, they put a soft focus filter in front of the telescope to make the brighter stars spread their light out. You can buy some very expensive filters. I've got some Leica soft tar filters for my camera. But in fact, black nylon stocking works pretty well. I got some rather dirty looks when I went to buy a pair of stockings the other day to do this. But seriously, it gives you this effect, and you see the colours much better. Now, the colour is telling us about the surface temperature of the star. The red stars are quite cool, 3,000 Kelvin. As you work up towards blue, you go through 4,500. Our sun is 6,000 Kelvin, that's its surface temperature. It's a yellow star. And then above that, we have the white stars and then the blue stars. So it's a massive range of temperature. And what, of course, is happening is that the body at a particular temperature gives you a certain colour. In the days before global warming, when we had some winters, I was a student and I was in digs in a place called Summertown, and I had a 1-bar electric fire. And I came home one day and you switch it on and you have a meter and you have a whole pile of shillings which seem to go about once every 5 minutes. And you sit there and you huddle around this, and I was trying to melt the icicles from my nose. Gradually it warms up, and you first of all feel a bit of heat. That's the infrared, that's what it's there for, of course. But then, of course, it begins to glow a dull red. That's about 800 Kelvin. But if you increase the temperature of something, then it glows. And as it gets hotter and hotter, the colour goes from red through orange, yellow, and so on. Now, to represent a star, the sun, last time you might remember I brought one of these eco-friendly bulbs, but they don't work the same way. So this time, I bought a real bulb, and I've tried to be good. I went down, I managed to get a 12-watt one. It's actually a little night light, which is quite handy because we had our grandkids to stay the other weekend. Now, if you can get the temperature of this up to something like, it's between 2,000 and 3,000 degrees, there's a chance it will then sort of glow. Now, whether I can do this or not, I don't know, but let's have a go. So if you get something at about 2,000 Kelvin, then in fact you'll get some light, and we see, that's gone out, I'm not very well charged there, am I? Anyway, so you can see some colour, and obviously the hotter it is, the bluer, the whiter it gets. Oxyacetylene arc welding, MIG welding goes up to about 20,000 Kelvin, and that's very blue. And you have to wear special goggles, because at that temperature, as is quite important for the rest of this afternoon, you get a lot of ultraviolet radiation. So just remember, the very hot stars, you'll see later, they're actually peaking in the ultraviolet. And these are the curves I wanted to point to you. If you have a cool star, in fact 2,000 Kelvin, this is the infrared. At 3,000 Kelvin, the peak is in the infrared, but you still get a fair bit of visible light. 3.5 there, 4,000, 5,000, our sun is up here a bit. And as you go higher still, this curve goes up and up and up, and it peaks in the ultraviolet. And there are two laws relating to this so-called black body radiation. It's what things, when they're hot, give out. The first one's called Wien's law. As you increase the temperature, can you see the peak goes to shorter wavelengths? The second one is, and I think it's pretty obvious, as you increase the temperature, the total energy increases dramatically. In fact, as the fourth power of the temperature. So if you double the temperature, you get 16 times more radiation coming off. So these very blue stars are giving off massive amounts of light, ultraviolet and infrared. Now, okay, our sun, we call it a yellow dwarf star. Where does the energy come from? So it has a surface temperature of 6,000 Kelvin. This really worried people. Up to the late 1800s, people had no real idea where that energy could come from. They knew how much energy the sun produced. It's quite a simple calculation. But if you said the sun was made of coal and there was enough oxygen to burn it, you could only keep the sun alight for something like 1,000 or so years. I think it was 1890 that Helmholtz, he realized that if you have a gas cloud, a ball of gas, which collapses down, obviously everything's getting closer together. And the energy which we call potential energy, which is the fact that something's up here, gets converted into kinetic energy as the whole thing gets closer together. Imagine a car at the top of a hill. If you push it down, it will start going faster and faster and faster. The potential energy it had at the top of the hill converts into kinetic energy. And if that hits something at the bottom, I think you can imagine a certain amount of heat will produce, not only on the brow of your husband or wife, depending who let the handbrake off. So essentially, you can power a ball of gas for about 20 million years, giving out the energy of the sun, if it gets gradually smaller. And because at that time they didn't know how old our solar system was, they were quite happy to think that 20 million years was enough. But then, in fact, in the late 1890s, people began to realize that the rocks on the Earth were much older than that. And it wasn't really until Einstein's special theory of relativity in 1905, with the most famous equation, I think, in the whole of astronomy or in physics, which is, thank you. Someone would like to come up here. E equals mc squared. That means, because c is very big, c squared is even bigger, and so a very small amount of mass could be converted into a large amount of energy. A little bit later on, they were able, about 1920, they were able to measure the mass of the proton and then the mass of helium. And it turns out the mass of helium is a little bit less than the mass of 4 protons. And it was realized that maybe you could take 4 protons and convert them into 1 helium nucleus, in so doing releasing energy. So we call this nuclear fusion. Well, that's actually a jolly difficult thing to do, seriously difficult, because protons have the same charge. What does that mean they do? They repel, don't they? And it's very hard to get two protons close enough together to get them to change into something else. It's called Coulomb repulsion. And even if you could sort of give them a temperature about 15 million Kelvin, where they'll be moving almost at the speed of light, under classical physics, you could not get nuclear fusion happening. The barrier is too great. And it was something called quantum mechanics that basically solved that problem. We can describe particles with something called a wave function. It's really a probability distribution. It says where you might find it. And if we have a proton coming towards another proton, there's a proton here, along comes a proton, it's got this terrible barrier, which it literally can't get over, I promise you. But when it's here, the wave function can actually go into the barrier, and it drops exponentially, and has a teeny little bit on the other side. And that means there's a very, very, very small chance that somehow that particle can burrow through the potential barrier. It's called quantum tunneling, and get close enough to the other proton so that what we call the nuclear strong force, which has a very, very short range, can come into play. This is a very slow process. A typical proton will wait about 10 to the 9th years, that's 1,000 million years, before reacting with another proton. Now, if you think about that, that's jolly important for us. Supposing it was only 10 to the 8th years, it happened 10 times more quickly. Our sun would burn up its fuel 10 times more quickly. We think it will last 10,000 million years. Fine. But if it was 10 times faster, it would be 1,000 million years. It would be dead by now. We wouldn't be here. So it's a good job that's a rather slow process. Well, we don't need to worry too much about what goes on, but basically two protons form the nucleus of something called a deuteron. It's the nucleus of heavy hydrogen. One of those plus another proton forms a light element, a light isotope of helium, and then we get two of those that combine together to form the alpha particle, which is the nucleus of stable helium. Just notice we get some gamma rays coming off, a positron comes off, that's an antiparticle. If a particle meets an antiparticle, what do they do? Annihilate, give off more gamma rays, at least two more. So we get a lot of gamma rays, and that provides the pressure that will stop the sun collapsing. But notice also we get a neutrino, electron neutrino. There are two other processes that go on. This produces about 80-odd% of the sun's energy. There are two slightly more complex processes, but the only important thing about those is that they produce some rather more energetic neutrinos, which is of interest later on. That energy has to get out from the core. Here's the core. The inner two-thirds of the sun, the energy actually in the form of photons, gamma rays to start with, work their way out by what's called almost a drunken walk. At every interaction they go off in a random direction. And finally, after about 100,000 years, they might reach here. It took me ages to do that. Anyway, they get here, and then we have convective zones that carry up the energy, firstly with some rather large ones, and then with some smaller ones, to the surface, the area we call the photosphere. So finally, after about 100,000 years, the energy in there gets out and it makes the surface hot. And the temperature of the surface will just increase in temperature. As it does so, the energy radiated goes up as the fourth power, and finally it stabilizes. And then, of course, that heat and light can reach us and keep us alive. So essentially, gravitational collapse is opposed by the radiation pressure, and the sun, happily for us, remains stable. Now, how much light and what colour a star ends up as it happens, depends on its mass. Two guys, Hertzsprung and Russell, produced a wonderful diagram, but I think it was 1919, independently. This is colour. We talked about colour, from red through to blue, and even ultraviolet over here. And these are the relatively faint stars. Our sun here, we always say, has a luminosity of 1. It's the sort of the thing we use as a reference. So these are fainter stars. We call all of these dwarfs. These are Brighter stars, we call them giants. And they all lie basically along that line here. The faint red stars down the bottom, the very bright blue stars up here. These can be 50 to 100,000 times brighter than our sun, and that's important as well. So that's called the main sequence. We'll come back to that later on. Oh yes, I was a great fan of Dad's Army. Don't get too worried, but not just yet. Now look, our sun's been around for 4.5 to 5,000 million years. I've said already, we think it will last for about 10. So can you see it's halfway through its life? So it's burned up half its fuel, has it not? Now, if you make a fire with fuel, when it burns up half of it, would you expect the intensity to drop? Isn't that what you might naturally expect to happen? Well, my friendly, that's I think what I've just said here. You might think that as the sun uses up its fuel, its brightness would decrease. But as my friendly bank manager told me, it doesn't work like that. It's actually rather interesting. As the number of protons reduces and the number of alpha particles, that's helium nuclei, increases, can you see the number of particles in the core gets less? For every helium, you've lost 4 protons. And the pressure of the core depends upon that factor as well as its temperature. In order to retain the same pressure and stop the star collapsing, the temperature has to rise. And that has a major effect upon the reaction rate of the 2 protons combining to form a deuteron. That's the key thing. So even though we have less fuel in the core of our sun, it is actually burning more brightly than it was when it was first formed, by about 30%. And it's going to continue to get brighter. So irrespective of global warming, etc., as time goes by, the sun will be getting hotter and the Earth will get hotter. Now, the time scale is quite long, but it could be, people argue, some people say 500 million years, some people say 1,000 or 2,000. But in fact, that is the thing that will prevent the Earth being suitable for life before the sun gets to the end of the period when it's burning hydrogen to helium. How many of you knew that? Because I found that quite surprising when I learnt about it. You don't ever learn anything, either when you had to give a lecture or write a book, and I was writing a book a while back, and it's interesting. Okay, so that's what I've just said. The sun is getting hotter. Just a little bit of interest. In the spectrum of the light of the sun, you see dark lines discovered in 1814, and it was found that they actually related to lines when you excite atoms on Earth. We used to sprinkle salt into a Bunsen burner and see the orange colour, sodium D lines. Well, they're there in the spectrum of the sun as well. I think actually it might be that pair, but don't worry. Okay, what was quite interesting, first of all, the different stars, and these are hot stars. Can you see the colour, the peak is sort of shifting down to the right? Well, these are the hot blue stars, these are the cool red. You can see most of the lights there. And can you see how the spectra changes? The lines you see depend very strongly on the temperature, which gives us a way of actually trying to classify them. We have 7 spectral types, O, B, A, F, G, K, and M. O is the hottest, M is the coolest. Now, I was taught by the reader of Astronomy at Oxford a lovely mnemonic for that, but I'm not allowed to say it anymore because it's politically incorrect. Seriously, I did once in a talk at Manchester some years ago to a group of ladies that had come from North Manchester, and they wrote to the Vice-Chancellor saying that I was... Did anybody know that? Can someone say it? A bit louder. Well, you could have a right now slap at the end, but no. In fact, if you say Guy, it's a little bit better. I haven't said it, have I? Anyway, that's how we all used to remember it. Now, basically, these are the types. The lines change, don't worry too much, but O, very hot, 30,000 Kelvin. As you come down to M, 3,000 Kelvin. Our star is a G star. Each of those groups is divided into 10, the hottest being G0, the coolest in this case being G9, and we're a G2. So we're the hotter end of the G-type stars, and those are the main classifications. Now, this is how many of the different types there are in the sky, in the galaxy. Have you heard it said that our star is an average star? Hands up, anybody's heard that said? Yeah, about half of you, or a third, isn't it? Rubbish. It's one of my hobby horses. Now look, I agree, we're a G-type star, O-B-A-F-G-K-M. Do you see we're below halfway, aren't we? But look at this. There are only 0.003% O stars, 0.13% B, 0.63% A, 3.1% F, and in fact we're about 3% down from the top of the Gs. Can you see there's only about 6 or 7% of all stars that are hotter and brighter than our sun? It may be a typical star, but it ain't an average one. So now you know. It's one of my, I'm a bit cross about that when people talk. So that's just what I've said here. Okay. Now a bit more physics. Remember I talked about the neutrinos that left the sun. They take 2% of the energy away, actually. And there are billions of them passing through all of us all the time. And someone decided he'd try and detect them. His name was Ray Davis, and he knew that a neutrino could react with the nucleus of chlorine to form a radioactive isotope of argon, which would then decay and could perhaps be detected by its radioactive decay. Now, you need a lot of chlorine, and so he built a tank here, pretty big tank, there he is, and that contained carbon tetrachloride. Can you see lots of chlorine nuclei in there? And in fact, in a month, about 10 reactions would happen, and he was able to detect about 10 argon radioactive argon atoms. The trouble was that was only a third of how many there should have been. Either we didn't know how the sun worked, or he wasn't doing his experiment properly. And most people just said, well, it's a difficult experiment, you're not doing it right. However, very happily, not that long ago, another experiment, in fact more than one, this is in Canada. This is in fact a 12-meter diameter sphere with I think 10,000 tons of heavy water. That means it contains the deuteron, the nucleus of hydrogen that you get in heavy water. It's actually nearly all the Canadian store, actually. It's worth an awful lot of money. And in fact, every day, 10 neutrinos would react with deuterons, and they actually cause some light, which can be detected by all these photomultiplier tubes. And that has totally vindicated Ray Davis's results. And very pleasingly, he was awarded the Nobel Prize for this work just a few years ago. Sadly, though, by that time, he was suffering from Alzheimer's disease and probably never knew that he got the Nobel Prize. It was very sad. But not only could this detect the electron neutrinos that come from the sun, you need to know there are two more. There are muon neutrinos and tau neutrinos, 3 types. We were only detecting 1/3. They changed the properties of this so it could detect all of them. And they found that the total number of neutrinos that come from the sun was right. It's just that they were split between the 3 different flavors. And what we think is happening, that neutrinos have a little bit of mass. And if they have mass, they experience time. And that allows them, the word we use is oscillate, to actually change between the 3 types of neutrinos, so that although all the ones that leave the sun are electron neutrinos, on their way between the sun and the earth, 2/3 of them will actually turn, half of them into mu neutrinos and half into tau neutrinos. So this actually has proven that neutrinos do have a very small mass, about 1,000th the mass of the electron. And that's quite significant for particle physics. There's been a nice story of nuclear fusion. Now, when eventually, it'll be another few thousand million years' time, the core of the sun is totally composed of helium, what happens next? Well, the obvious thing to happen is for 2 helium nuclei to combine together to form a nucleus of beryllium-8. But thank goodness, beryllium-8 is incredibly unstable, and it doesn't really happen. If it did, stars wouldn't have a long, stable phase where they stay roughly the same temperature. So how can you get beyond that? Well, this is also not that easy. And this is where Fred Hoyle comes. I'm sure you're all aware of Fred Hoyle, wonderful British astronomer and physicist. If you could finally increase the temperature of the core of the star to about 100 million degrees, it's possible to get what they call the triple alpha process, where 2 helium nuclei come together, form beryllium. But before the beryllium has a chance to decay, another one comes along, that makes 3 triple alpha to give you carbon. But there is a fundamental problem. The energy of those alpha particles will be too high, and that carbon nucleus will just break up. There's too much energy involved. There had to be something to make that reaction work. And this is what Hoyle said. Since carbon is so common, we are made, we're carbon-based life, the stars must have discovered a highly effective way of making it. And I'm going to look for it. And he came up with an idea, which I'm trying to illustrate in these 2 rather simple diagrams. This is a trampoline. It's obviously an old one because it doesn't have big safety guards all around it. Here we have a ledge, and we have a person on this ledge who's going to drop down, bounce off, and this is another ledge which he's got to get to. But the point I want to make is that nothing he can do can get him to land on that ledge because he's got too much energy and he'll just go over the top. Can you sort of vaguely appreciate that? Right. Hoyle said there must be a way to get onto that ledge. Can anybody think of what you could do to get him onto that ledge? No? The ledge will stay where it is.
Wait.
Put a little bar up here. So as he flies over the top, he holds onto the bar, he oscillates a bit, and then can drop down. Correct? So what Hoyle said, there has to be an excited state of carbon at just the right energy, just the energy, the 3 helium nuclei, so the carbon can exist in that state for a while, not break up, give off probably a gamma ray, and drop down to the state where carbon's stable. Did you see that? And no one believed that was possible. Now, Hoyle could be rather obnoxious at times. I don't know if anyone's read that, but he could. And he went to someone called Geoffrey Fowler, who was at Caltech, and said, I want you to look for a resonance which is above what we call the ground state of carbon, and it's got to be this, otherwise we cannot make carbon. And eventually he badgered Fowler so much, Fowler got fed up and said, all right, we'll do it. It took them 6 months to do, and they discovered a resonance within 5% of the value predicted by Hoyle. It's called the Hoyle resonance now. And that's how carbon can be produced. Now, can you see that's pretty important for us as well? A lot of us is carbon. If you couldn't make carbon, stars could not then make all the other elements. In fact, from carbon, it's actually quite easy to get. Carbon's 12, what's 16? Right, 1 helium plus carbon gives you oxygen. Another helium plus oxygen gives you neon. Another helium with neon 20 gives you magnesium 24. Another helium gives you silicon 28. Now, because the number of protons is going up, it gets harder and harder for that to happen. And in stars like our Sun, that's really as far as nuclear fusion goes. You get some of the intermediate elements as well, of course. But those particular ones are particularly common, which is why silicon, right, is quite common. Not sand about, you might have noticed. Okay, so that's a major piece of work that was done by Hoyle. He went on to work out how all this happened, and it really is not very good that Hoyle did not get a Nobel Prize. William Fowler did, Hoyle didn't. Some people say it's because he made a hell of a fuss about the fact that a lovely lady called Jocelyn Bell didn't get one, and I'll be telling you her story, in fact, I think next time. So that's what happens. Basically, 2 helium nuclei come together to form beryllium, another one very quickly interacts, and we get carbon-12. And when this starts happening, stars get bigger. Our sun will envelop the Earth. Don't worry, we won't be around then. We'll have gone because of this heating up of the sun before then. And essentially, we see these so-called red giants. And this is one of these pictures that's been done with the stocking in front of the lens. And you see the stars, the bright stars are particularly large. This one is very red. It's Betelgeuse. It's actually a very big giant, red giant. We call it a supergiant. And this is a lovely constellation. That's the end state of stars, but I now want to say something about how stars form. And below the 3 stars of Orion's belt, in fact, I saw that when I woke up at 5 o'clock this morning. You hope you're going to sleep in, don't you, when you're doing a thing like this? I hope you don't. Anyway, down here is the region called the Orion Nebula. And that's one photograph of it, and you can begin to see some red coloration. This is the most beautiful object in the heavens, and if it's ever clear and I've got my telescope out, I can spend 20 minutes just looking at it. And here's a lovely picture. This is the central region, and it's being lit up by the light from, in fact, 6 stars, but 4 are particularly bright. They're called the trapezium, which are actually here. And this is all dust and gas. And it's out of that dust and gas that those stars have formed. So the light just comes from the stars, but you see the red colour as well. Look at this picture. Beautiful coloration. And I think, can you just see the 4 stars in the middle there? I may say you had to cheat to get pictures like this because they're so bright. What you do is you take a short exposure to get that bit and a long exposure to get that, and you combine them together in something called Photoshop. Otherwise, you just can't show it. But that's a wonderful image. But look at that lovely red colour. Now, where does that colour come from? Remember, these very hot blue stars give off lots of ultraviolet light. That's very energetic. If you have a little hydrogen atom sitting there, just, comfy and happy with itself, then what that ultraviolet photon can do is to kick the electron, sometimes even out of the orbits that it can hold around the nucleus, but certainly up. And then in time, they cascade back down again. And these are called transitions, and 2 of them are important to us. From that transition there to that one, which happens not that often, you get a rather lovely greeny blue colour. But the one that's really important to us, this one to there, you get this reddish colour. It's called the hydrogen alpha line, and that's the colour we're seeing. Now, the point is, can you see you can only get that colour when you have ultraviolet light? You only ever see that lovely red colour in the sky near young, hot blue stars. So these regions are stellar nurseries because these very hot stars only live for a few million, 10 to 20 million years, so they're very young. We can get special filters just to let that light through so we see things more clearly. This is in fact looking right at the trapezium here. There are the stars. And that's even a picture I took, not a very good one, but it just shows you the trapezium here and the 3 stars in the back. That's what you can see with a medium-sized telescope. Now, these are the 3 stars of Orion's belt. And just below them, can you see this sort of reddish, pinky red colour here? And a little bit of a horse's head, it's called. Let's look in more detail. You know the rook? No, the knight, rather, on the chessboard is here. And this is a dust cloud, which is why we don't see any stars there, which is basically preventing the light from the hydrogen reaching us. A little bit of a jet of dust that's climbed out of that cloud, probably pushed out by a young star. Now, you see the colours vary a bit. You have to sort of tweak that to your own, best way it looks best. But that's a lovely picture showing the dust that makes up the so-called Horsehead Nebula. And somewhere deep in that dust cloud will be a star. When they're young, they blow off a lot of material, pushing the dust out of the cloud. Okay. Going to the Summer Triangle, the brightest star in Cygnus the Swan is Deneb. There's a lovely region of nebulosity just to the left of that. As you'll see, because it looks like North America, it's called the North American Nebula. That's Deneb there, by the way, and it's a bit over to the left. Sadly, our eyes are not very sensitive to the red. And it's jolly, jolly hard to see. It's easy to photograph, but hard to see. And I've never seen it, although one of my friends reckons he has. We keep ribbing about that. But look, does that look a little bit like North America? When I first went there, I didn't want to fly. This was a long time ago, and I thought the shortest way and the least chance of hitting anything would be to fly from Prestwick to Boston. You could do that. This is a long time ago. So I did, and then I got a Greyhound bus to come all the way down here, and I got out of the bus at Fort Lauderdale, and the first thing I saw was a bird standing on a pole. Any guess what it might have been? There's one here. The eye and the beak of a pelican. That's the pelican. Do you see? Quite a good pelican there. So look, the fact we see this lovely red colour tells us that we have young stars, that ultraviolet light is exciting the gas. Now, this is another lovely region, and I'm going to come to a picture that you'll know. This is called the Eagle Nebula, and these are two pictures using this H-alpha. Can you see the head of the eagle, his talons, and the fish, and his wings? You see that? Now, we have other clever filters that just pick up some of these lines. This picks up a line of oxygen in the green. And what people are beginning to do, it was started by the Hubble Space Telescope, is to take false colour images using these narrow-band filters that show a lot of detail. And that's the same region. Do you see the eagle? But do you agree the colours are quite different? They're not real colours, but we're seeing a lot of pictures looking like this because they show detail fantastically. And that's a close-up again. And this is the picture. Have you all seen that picture? It's called the Pillars of Creation, a Hubble image, and it's showing these dust clouds. That's the fish. Actually, it's even got some teeth on see the talons there. It's got some claws. Not like an eagle, but nevertheless, you get the idea. And this is, in fact, a region where stars are forming. But we're now getting some of these slightly odd colours, but nevertheless, they look very lovely. Now, when those very hot stars burn up their fuel very quickly and die, there's no more ultraviolet. You don't see the red coloration. And what we then see are the stars that were formed in that stellar nursery. We call them open clusters. And in the constellation of Taurus, Orion, that we taught is down here, this is the cluster called the Hyades, and this is the Pleiades. And they're lovely things to look at with binoculars. Now, I should just say that that bright star, which is called Aldebaran, which is an orange giant, has got nothing to do with the cluster. They're all going that way, and Aldebaran's going down that way. It's about half the distance. So if you can just ignore that, then this is the Hyades, and this is the Pleiades. Now just notice, we'll come to it again, can you see there's some red stars there, or orangey red stars? Can you see any there? Don't think you can. Let's look at that. They're all blue stars. Now this is one of the most wonderful individual images I think there is of the heavens because it tells us so much. Okay, these are hot blue stars, fine. But we see this lovely red blue coloration. We believe the cluster is moving through a cloud of dust, and that dust is reflecting the light. And in the same way that dust, we see the sky blue and the sunlight coming through the atmosphere is reddened, particularly if there's a lot of dust in the atmosphere. Blue light reflects the light very well. The red light is not so easily reflected. So those dust particles give us a blue coloration. Partly because the light is blue, partly because dust scatters blue light preferentially to red. But look, that's not all. The nicest things about this, can you see detail in that reflection nebula it's called? Do you see those striations? That tells us an awful lot. Something there in that dust has to have a sense of direction. Otherwise, you couldn't do that. What things do we know of that have senses of direction? And what might we use? Compass. This works because it's a ferromagnetic material. That tells us that in that dust there must be iron or iron compounds. You see that? Otherwise, unless there's some other thing we don't know about that can, line up with something. So first of all, there's going to be iron there. But also, someone's already mentioned it. Can you see it's got to have a thing to line up with? The galaxy must have a magnetic field. And that's what we're seeing here. It's like sprinkling iron filings, but these things are reflecting the light, and these striations tell us about the magnetic field. So we can learn an awful lot from that. These are two other clusters, the double cluster in Perseus. Notice that one's got a fair number of reddish stars, that one perhaps less so. M35 in Gemini. There's a couple of orange stars there, a much smaller little cluster down the bottom there. And the Beehive cluster in Cancer. Again, these are fairly bright orange-red stars. Now, remember I showed you a little plot where all stars were? Well, this is what you get. If you make a whole group of stars of different sizes, they all lie along this line called the main sequence. But these big stars don't live very long, and they tend to become red giants, and they move over this way, and they will then die. And if you have something that's old, you get the bottom bit of this, but can you see all of these are becoming red giants? So that plot can tell us the age of these particular clusters. Here's one, okay, there's got some blue stars, but there's some lovely red-orange stars as well. This is a plot of the Pleiades, and can you see it's pretty well lying along the main sequence? This is a very young cluster, probably less than 115 million years old. But if you look at the Hyades, those are the two I showed you together, the top bit has disappeared. Can you see these are sort of coming over a bit? And we've got these red giants over here. So looking at these, the colour actually translates to age. That's quite nice, because we can age different things across the galaxy. How will our sun die? Well, eventually, when it's got the cores become silicon, as far as it can go, the whole thing changes. There's nothing that can really stop the mass of the star contracting that central core. And it contracts right down until it's about the size of the Earth. There's something that stops it contracting further. A bit more of that in the next talk. It's called electron degeneracy pressure, but don't worry about that. Basically, when the sun's mass, or the mass of the core, gets to about the size of the Earth, that's it. It stops. It's called a white dwarf. It's very hot. It's like the ember of a nuclear furnace, and they're incredibly hot to start with and cool very slowly. But the outer parts of that star are blown off, and they give us some of the most beautiful objects we can see in the heavens. Again, our summer triangle. There are two of these objects, perhaps two of the best in the northern sky here. This is Lyra. There's Vega. That's Vega. Two little stars down there. That's that one and that one. And between them is something called the Ring Nebula. We'll see in a second. And just above, this little thing is called Stagger to the Arrow. About there's another one called the Dumbbell Nebula. And there's the Ring Nebula. It's absolutely beautiful. It looks like a little donut to the eye. Possibly you can see a touch of green with a big telescope. This is a very, very faint star. You need a pretty big telescope under ideal conditions to see it. I think a few of my friends and I saw it in the Isle of Man with a 16-inch telescope. But it's very hard to see. But you can easily see this ring. Now notice the colours. The red, the excited hydrogen. Okay, we've got some blue, that can be hydrogen as well. But also oxygen gives rise to blue and green lines. And we're seeing that there. The oxygen that we're breathing in this room today has come from the explosions of stars like our sun. And actually, it's pretty miraculous if you think about it. It's no good making all the elements from which we're made in stars unless those stars blow up, right? If they don't spread that material around the galaxy, we couldn't be here. And this is the Dumbbell Nebula, the second one I mentioned, and that's the central white dwarf star, and here is the outer part. There's a lot of green actually here, and I've seen that through that sun telescope that night, and it looked like an iridescent green. It's really the only thing I've ever seen dramatically showing any colour through a telescope. This is a lovely one. Do you remember last time, those were here, I talked about the Earl of Rosse in County Offaly with his lovely telescope. He made some wonderful drawings, and this is a drawing he made of the Owl Nebula. Do you see the Owl Nebula? Like, quite why that star got to there, I don't know, but it does look rather lovely, doesn't it? So that's another planetary nebula, the Owl Nebula. This is called the Helix Nebula. You can see the central star, the white dwarf is there. Very dramatic one there, taken by the Hubble telescope. I rather like this one. It looks like a little sort of a soap bubble, doesn't it? And in fact, sometimes, although it looks spherical, it's because we're looking down a cylinder. And that one's, we might call that one the Christmas Cracker Nebula, but we're looking at it sort of sideways. It's all to do with magnetic fields. Perhaps one of the most interesting is actually in the constellation of Gemini, the twins. This is called the Eskimo or the Clown Nebula. Can you see the face? I've had the nose is a bit sort of high, but this is the ruff, you know, the parka, the lovely sort of furry bit around here. You know, the clown has that white outfit with the red ruff. Those are the two things that sort of represents. So we do see, those are some of the prettiest things we see. They're called planetary nebula because they look, through not a very good telescope, as little discs, they look a little bit like planets. They're not, they're the end stages of the life of stars like our own sun. Now, what can we see if we go beyond our local environment? We look at the galaxy as a whole and then beyond it. Rather lovely picture. It's not really dark enough, but the Milky Way, it's rather, isn't it nice how the little way here goes on into the Milky Way? If we look at that in close-up, we see these pinky red regions. What's that tell us? Those are regions of star formation, stellar nurseries, and we have lots of them along the plane of our Milky Way. And we actually see some little star clusters as well. That's one where you can still see a little bit of the red nebulosity. So we see these colours in our own galaxy. Nearby, we have the Large Magellanic Cloud, about 150,000 light years away. This is one of the largest star-forming regions we know of. I mentioned a supernova there last time. This is the Tarantula Nebula, because it looks a little bit like a spider. I always remember James Bond and Dr. No in the spider. But I was at a rather sort of an age when you appreciate such things as a teenager. I won't say what else was good in that film, but anyway, this was the spider bit. And in fact, the supernova was about there, actually. So again, we're seeing the red coloration. This is the Small Magellanic Cloud, star clusters, and these stellar nurseries. We see them everywhere. M33 is the third largest galaxy in our local group. There and there we've got two massive, absolutely massive star formation regions. There's a pair of galaxies in Ursa Major, M82, M81. Just look at this picture. Now, again, it's not very dark, but does it not appear as though that is rather orangey yellow light, whereas the spiral arms look rather more bluish? Does that sound... It's better perhaps from where you are than I am. Now, why is this? In the centre of a galaxy, we basically are left with old stars. But in the spiral arms, those are regions where stars are being formed today. And because a single blue star can be 50,000 times brighter than our sun and vastly brighter than little faint red dwarfs, can you see that a relatively few number of blue stars can outshine all the rest? So we get that blue colour. So we see this rather beautifully there, and I think the next slide shows it as well. I love it. It's better on my screen, I'm afraid, but that's a lovely orangey yellow colour, and these are very obviously blue spiral arms. And again, in there, you can see some star-forming regions, not quite so obviously. So the things that we see locally, we see throughout the universe. We believe that everywhere we see, things basically work the same way. Lastly, M51, the Whirlpool Galaxy, that was the one that the spiral arm structure was shown by the third Earl of Rosse. There's a lovely image taken by the Hubble Space Telescope of the central part of this, and look at this whole string of star-forming regions. This spiral arm is producing lots and lots of stars. In some galaxies, that process goes on to a very great extent. We call them starburst galaxies. Now, because there are lots and lots of very young stars there, there's lots of ultraviolet light. We now have ultraviolet telescopes in space, and they see this as a lovely ring around the nucleus. So that's the same picture as that, but in the ultraviolet. So we can look at these starburst galaxies. So our universe is still alive, things are going on. Okay, I believe, as Professor of Astronomy, I'm also meant to include some physics and maybe even some chemistry. And I had a sort of feeling that our academic registrar maybe have a little black book about, has he covered any physics in this lecture? Well, look, you've had some quantum mechanics, some nuclear physics and some particle physics, and now you're going to get some metaphysics. So I hope she can tick the physics box. I've actually measured probably 8 different chemical elements. I'm not sure that counts or not. Okay, metaphysics. Look, there are quite a number of things that I've actually mentioned in the talk tonight, which maybe indicate that there are quite a number of things that have had to have happened just right, otherwise we couldn't be here. Have you got that sort of feeling? I've tried. There are lots and lots more, seriously, and I might, probably the very last lecture, I might spend the whole lecture talking about this thing. Our universe is just right for life. Obviously, if it wasn't, we wouldn't be here talking about it. But there's nothing in the laws of physics that says that must be so. We don't think things happen, just like that. How can that be? Well, there are probably three possibilities. One is that there is a creator, some beings in a higher universe that have made a universe which has the right properties for us to exist in. And if that were the case, I sometimes think that in the same way that a great musician who produces a symphony, or an artist that produces a great piece of art, what's the point of doing it if there's not anybody there to see it, to look at it? So maybe one of our roles here is in fact to be able to appreciate the beauty of our universe, as you've hopefully just seen. So that's one possibility. Another possibility is that there are myriads of universes. The Sonny Royal, Lord Rees, calls it a multiverse. Now, we live in what we call the universe, and we have a limited view. We can only see as far away as the light has reached us. That's our visible universe. Beyond that, we really don't know what happens. Actually, we use that name, we actually say the cosmos for that, so my title was really not quite right, because the cosmos, we can't see all the cosmos, we can just see our bit of the universe, but it made a nice title, that's why I used it. Okay, now beyond the bit of the universe we can see, things might be different. And you could have different regions where the properties, the laws of physics, or actually the constants of nature are a bit different. Some of those could be okay for life. You see, unless it's done by design, then there have to be myriads of universes, all different properties, and one or two or more may be suitable. Now, there's another possibility. People have been worried about the fact that gravity, which we'll talk about next after Christmas, is a classical theory. Quantum mechanics covers everything else. Somehow they've got to be combined. People are working on what are called string theories. There were basically 5 theories, all of which have 10 dimensions. 6 of them are all curled up to be very small, and they make up the particles. And these strings, as they vibrate differently, in the same way a violin string can vibrate at different harmonics, these can represent different particles. You've probably never heard of who I believe is the most brilliant physicist alive today. His name's Ed Witten. Hands up, anyone who's ever heard of him? Oh, okay, he does exist. And he showed a few years ago, I think it was 99, that all of those theories could be put into an outer theory. He calls it M theory for mysterious, mother. Some people say it's W upside down, but that's unfair. And basically that is a theory of 11 dimensions. And it could be that we are, in R10, we're just one of myriads of universes that exist in this further dimension. You might have wondered why I brought a loaf this morning, 7 o'clock, before I left. I won't take it all apart. Can I just take some of it out? Would you agree that that is a 3-dimensional object? Yes? Okay, we can see that. Now, I managed to borrow one of these. If I put this through, and I now separate these pieces of slices of bread. I should be careful not with my supper tonight. Now, supposing I took some ants or some little grubs you use for fishing. I was going to buy some, but I couldn't find any fishing shops in High Holborn. They're probably not too close to town. Now, if you put those ants on these individual little bits of bread, they would effectively be living in a 2-dimensional universe, wouldn't they? They probably wouldn't have, I don't know how far ants can see, but they probably wouldn't know that there are other ants here or there or there. Do you see that? So what we can see is what to ants would be their own 2-dimensional universes are in fact all part of a 3-dimensional universe. So in the same way, ours could be just one, it's a 10-dimensional universe perhaps, but in another dimension. Now I cannot tell you which of those 3 possibilities might be right, or even if any of them are right. All I can say is that at least one universe has become suitable for the evolution of life, as us, giving us the chance to look at some of the wonders, the beauty of the universe, and try and learn about it. And I do hope you'll come again over the next couple of years or so and hopefully learn a bit more. Thank you very much. Thank you.